Hello everyone. In this work, we have studied some properties of the Le2-BASN-SE4 compound, such as structural, elastic, electronic, and optical properties. This exhibit presented according to the following plan. After a general introduction, in which we present our problematic, we present our material. This part will be followed by a part of result and discussion, and we end this presentation with our conclusion and our perspective. Introduction. The search for new materials with specific physical and/or chemical properties is a major challenge in today's industry. One of the examples that can be given is the search for so-called diamond-like semiconductor (DLS) materials. They have been the subject of intense research in the field of photovoltaic, nonlinear optic, thermoelectric, and spintronic. Binary and ternary DLS materials have been sufficiently studied, unlike quaternary materials. These quaternary compounds do not have as much interest due to the difficulty of their synthesis. A lot of research on quaternary compounds of type 1,2, 2, 4, and 6,4 has been reported, and recently the materials Le2-BASN-SE4 has been synthesized. The interesting physical properties and possible technological application motivated use to contribute to the study of some unexplored physico-chemical properties of our compound, such as structural, elastic, electronic, and optical properties, using the full potential linearized augmented plane wave within the framework of the density functional theory, and we treat the exchange correlation energy by the GGA-WC approximation and by TBMBG to correct the fundamental gap. Presentation of the material. Binary 2,6 semiconductor generally crystallized in a zinc blende or Wurtzite structure. When the cations of the group 2 are replaced by cations of group 1 and 3, the binary structure, zinc blende, mutates into ternary structure. The first is the chalcopyrite structure, and the other is the type structure CuIu. When the group 3 cation is replaced by pair 2 and 4 internally chalcogenide, chalcopyrite 1, 3, and 6,2 mutate exclusively in the K-street configuration. On the other hand, there are two possible configurations for the same replacement in CuIu type structure, one leading to the stannite structure and the other leading to the PMCA structure. In our work, we studied our compound in these three structures: K-street, stannite, and PMCA. Results and discussions. The knowledge of the total energy of this material allows you to know the most stable structure. This figure shows the variation of the total energies with respect to volume and for different phase adjusted using the Birch-Bernagin equation of state. The result found show the most stable phase is stannite, while the least stable phase is PMCA. The following table summarizes the ground state parameters such as atomic coordinated, lattice constant, bulk modulus, and pressure derivative of bulk modulus. As can be seen, the result obtained for the stannite structure agree with the available experimental data. For the other structure, K-street and PMCA, we have no data for comparison. Since the stannite phase is the most stable, we wanted to study the other properties, elastic, electronic, and optical, in this structure only. Elastic properties. In the stannite phase and for the tetragonal structure, the number of constant CEJ reduced to the 6 independent components. The result obtained show that all the constant CEG are positive and satisfy the generalized criteria of mechanical stability. Therefore, our compound is mechanically stable. We see that C11 greater than C33, and please that the bonding strength along the 100 and 010 direction is stronger than that of the bonding along the 001 direction. C66 greater than C44, suggesting that the 100-010 shear is more difficult than the 100-001 shear. The second table summarizes the elastic parameters calculated. From these parameters, we can draw the following conclusion. The elastic anisotropy equal 0.099 So we can say that our material is almost isotropic. Young modulus is around 243, so this compound has a fairly low stiffness. The Pass indicator ratio is greater than the critical value. Then this compound is ductile material. The Poisson ratio is greater than 2.25, so we can say that this compound presents a considerable ionic contribution to the interatomic band. For electronic properties, we start with the band structure. The band structure of our compound calculated using the TBM-BG approximation are shown in the following figure. From this figure, we can see that the maximum of the valence band, VBM, and the minimum of the conduction band, CBM, is located at point Z. This indicates that our compound is a direct gap semiconductor of 2.19 electron volt. Our simulated gap, as well as other theoretical and experimental results, are given in this table. The value of the gap are in good agreement with the value obtained by experience. To better study the nature of the electronic band structure, we also calculated the total and partial densities of state of this compound. We have divided the density of state into 4 regions. 2 regions for the valence band, VB1 and VB2, separated by a 2 electron volt gap, and also 2 regions for the conduction band, CB1 and CB2, separated by a gap of 0.7 electron volt. The contribution of the orbital of each atom and for the 4 regions is summarized in this table. For optical properties, we use only the imaginary part of dielectric function. The role of this part is that it's allowed to describe all the interbond transition. The following figures show the imaginary part of a dielectric function calculated in the energy interval 0.13 electron volt. We note that epsilon 2 exhibits a relatively marked anisotropy in the range of energies 5 and 12 electron volt. Thus, we can see that epsilon 2 is partially 0 up to value A0 equal 2.19 electron volt, which correspond to the value of the gap. Beyond the value A0, we distinguished on the curve different region that we name it A, B, C. This region signifies the presence of the significant absorption phenomenon. The following table summarizes the possible interbond transition. Conclusion and perspectives. Conclusion. The calculated structural data are consistent with the available experimental result. From our calculated elastic constant, this material is mechanically stable, could be classified as ductile materials. The calculation of the band structure reveals that our compound has a direct band gap with value of 2.19 electron volt. For optical properties, and in this presentation we have explored the complex dielectric function, and we show non-considerable optical anisotropy in the XX and ZZ polarization direction. Analysis of the imaginary part, epsilon 2, confirm the existence of an energy gap between the maximum of the valence band and the minimum of the conduction band. Perspectives. To continue the study of the Le2BAS and Se4 materials by exploring its nonlinear optical, thermoelectric and thermodynamic properties, as well as the search of new DLS materials. Thank you for your attention.